Hi everybody, I'm Doug Daniel, flight instructor, founder of the Pilot's Workshop, author of Flying Secrets. Today we talk about how wings work. If I use some terms that you're not familiar with, I got another video that you can look at that'll explain them all to you. Just go to privatepilottrainingonline.org and you can find all the videos you're interested in. Having said that, let's get to it. Okay, I'm going to demonstrate a wing that has no angle of attack and no camber. I'm going to blow wind over it from left to right, and let's see what happens. It appears to have drag. However, it could have blown out of the way so quickly that we can't tell if it has lift or not. So let me overcome the drag with a drag resistant device. And now, let's put it back in the wind tunnel. Blowing as hard as I can, nothing happens. Okay, we have another wing that has camber. I will blow on this wing about as hard as I did the other time. As you can see, it has lift. I'm sure it has drag as well, but there was no angle of attack. You saw wind over a flat surface produce drag but not lift. Wing over a curved surface produce lift, and wind does not need to pass under a surface to produce lift. I have had many students confused by some of these widely repeated but incorrect statements. Bernoulli's principle does not say that the faster the wind blows over a surface, the lower the pressure on the surface. Two air molecules that separate at the leading edge do not have to meet at the trailing edge. I am telling you this because some of an airplane's flight instruments would not work if these theories were true. Now to set the record straight. Air molecules passing over the wing follow a much more curved path that pulls them away from the wing, lowering the pressure on the upper side. Air molecules passing under the wing follow a curved path that initially pushes them toward the wing, raising the pressure on the lower surface, then gently pulling them away from the surface. The accumulated effect on both surfaces produces upward lift. If the angle of attack gets too high, the air can no longer follow the upper surface and the wing loses its lift quite abruptly. I want to show this to you with some real wind tunnel results. You are looking at a wind tunnel in the Mechanical Engineering Department of Cambridge University, Cambridge, England. The wind is blowing from left to right. The wind velocity is the same from the top of the tunnel to the bottom. The lines you see are trails of smoke that are evenly spaced vertically. That is, evenly spaced vertically when they enter the wind tunnel. Not surprising, these smoke trails are called streamlines. In the middle of the picture you can see the outline of a wing with constant cross-section called an airfoil. In this picture, the airfoil has a very slight positive angle of attack, but you can see the influence that slight angle has on the airflow. Even before the wind reaches the leading edge of the wing, it is rising. After it passes the airfoil, it continues its downward trend. In this picture, the angle of attack has been increased to near its critical angle of attack. That's the angle at which the airflow can no longer stay attached to the upper surface. We can tell that the wing is not quite at its critical angle because the flow is still attached to the upper surface and is flowing past the wing smoothly. Notice the influence that the airfoil has on the wind well before and well after the air passes the wing. Also notice that the air goes around its tightest curve above the wing, slightly aft of the leading edge, right in there. Interestingly, the streamlines squeeze together in that same region. This is the region of maximum lift. Let me explain why. The only way that streamlines can be closest is for the wind to be the fastest in that region. We know that the higher the speed or the tighter the curve, the greater the centrifugal force. Since the air moving through this region is at its fastest and is following its most curved path, it must be subjected to its maximum centrifugal force. The centrifugal force pulls the air away from the wing, minimizing the air pressure on the upper forward surface and making that region the highest lift region of the wing. Applying the same logic, you can easily see how the wind pushes at the bottom of the wing. And only so slightly right in here pulls away from it because of that slight curvature following the surface of the airfoil. I want to show you some physical evidence that the wind blows much harder over the top of the wing than the bottom. Even though the airfoil is hard to see, it's still there and at the same angle of attack. In this series of pictures, our benefactor in England is sending puffs of smoke in the tunnel. All have been released at the same time, but even in this particular picture they are not lined up because the wind that is impending on the wing has been slowed down by the wing. In this picture you can see that the wing is pushing back on the wind and slowing it down even before it reaches the leading edge. Now the puffs have reached the leading edge. See how much further ahead the smoke is above the wing than below it. We can only conclude that it's moving faster above the wing than below the wing. The speed difference is even more dramatic here. This image shows how much the wing drags on the air, especially near the surface. See, this is way ahead up here than it is real close to the surface right in there. And on the lower surface is even more dramatic. Here's this puff that is still resting almost against the leading edge, and as we move further from the airfoil, the wind is obviously blowing faster. And this is even more dramatic, showing how much faster the wind is down here on the bottom than it is close to the airfoil. Over here it's really moving right along. Okay, we're going to increase the angle of attack until we get flow separation. We get flow separation, we're going to have stall. Okay, he's increasing the angle of attack very slowly. Now we're starting to get some burbling. You can see it back here. And then as he increases it more and more, pretty soon we'll just have complete and total separation. There, that wing is severely and totally stalled out, and so it's not creating any lift whatsoever. And it happens very abruptly. Thanks for watching. Meet me at privatepilottrainingonline.org. And here's a normal healthy flow. I've got some more videos for you. Except for you be sure to leave a comment on the blog so I know what you want, what you like, and what you don't like. There it is. Take care, and see you later. Went from an attached flow to a stall very, very quickly. Okay, thank you, Cambridge.